Welcome to part 3 of 3 on dividing polynomials. This section will emphasize two important theorems. The first we'll look at is called the remainder theorem. If the polynomial p of x is divided by x minus c, then the remainder is the value p of c. If we use the example to evaluate p of x equals x to the fourth minus 10x to the second minus 2x plus 4 at negative 3, we would have the following. My divisor is negative 3. I need to list all my coefficients. X to the fourth has a coefficient of 1. X to the third has a coefficient of 0. Negative 10x to the second has a coefficient of negative 10. X to the first has a coefficient of negative 2, and the constant term is 4. Performing synthetic division will drop the 1 down and multiply by the negative 3. That will give me negative 3. 0 plus negative 3 is negative 3. Negative 3 times negative 3 is 9. Negative 10 plus 9 is negative 1. Negative 3 times negative 1 is positive 3, and negative 2 plus 3 is 1. Negative 3 times 1 is negative 3, and we have a remainder of 1. Does this look familiar? The remainder is 1, so we can say that p of negative 3 equals 1. And for demonstration purposes only, we have p of negative 3 would be the same if we substituted negative 3 in for x and calculated what you get. It'll come out exactly the same. So let's use the remainder theorem to evaluate f of x equals 3x to the third plus 8x squared plus 5x minus 7 at x equals negative 2. Our leading coefficients are 3, 8, 5, and negative 7. Using synthetic division, we drop the first coefficient down and multiply by the divisor number. Negative 2 times 3 is negative 6. 8 plus negative 3 is 2. Negative 2 times 2 is negative 4. And 5 plus negative 4 is 1. Negative 2 times 1 is negative 2. And my remainder is negative 9. Since negative 9 is my remainder, I can say that f of negative 2 is equal to negative 9. This is the basic idea behind the remainder theorem. A number that we use to divide the polynomial by can also be related very directly to a substitution into the function itself to find a range value. It doesn't seem like these two operations would be related, but they very much are related to each other. This will help us moving forward with being able to quickly identify whether a number is a root or 0 of the polynomial or not. Now let's look at the factor theorem. The factor theorem says that c is a 0 of p if and only if x minus c is a factor of p of x. These very clearly relate to each other. Before, we were just showing you that if you have a remainder, it's the same as substituting the divisor into your polynomial. But in this case, it's showing you that if your substitution number gives you a 0 as an output, a range value, then it is a factor of the polynomial p of x. And so we can use the previous theorem plus the factor theorem to identify the factors of a polynomial. Let's show that -1 is a root, or 0, of the polynomial 2x to the third plus x squared minus 7x minus 6. Using synthetic division, we will drop the 2 down, multiply by -1 to get -2. 1 minus 2 is -1. -1 times -1 is 1. -7 plus 1 is -6. -1 times -6 is +6. And we do indeed get a 0 as our remainder, which tells me that p of -1 equals 0 and x plus 1 is a factor of p of x. So p of x can equal x plus 1 times the remainder. Since the 0 is our remainder, -6 is our constant term, -1 is our x to the first term coefficient, and 2 is our x to the second term coefficient. So we can write this as a product of the factor we divided out times 2x squared minus x minus 6. This will come in very handy moving forward. This is a very cool way to check to see if you have factors in a polynomial. You can move forward from there. So now let's kind of switch gears here. Now we're going to be given the zeros of a polynomial, and we're asked to find the polynomial itself. In this first example, we are told that the polynomial needs to be found of degree 4 that has 4 zeros, 0, -3/2, 3, and -2, and has a leading coefficient of 9. We'll have to do some tricky stuff at the end to get a coefficient of 9, but let's just start out with identifying these zeros and what to do with them. We're going to say x equals 0, x equals -3/2, x equals 3, and x equals -2. Now set each one of these factors, or zeros, equal to 0, so we're forcing them to be zeros. So we just have x equals 0, that one didn't change. Now this one's a little tricky. If we want it to be a pretty binomial, we would multiply both sides by 2 first. So that would give me a 2x plus 3 equals 0, and if this is weirding you out a little bit, just solve for x again, and you will see that it comes out as -3/2. X minus 3 equals 0, and x plus 2 equals 0. The last part of this is to rewrite them and figure out what number will need to be in front to make my leading coefficient 9. I'll have an x, I'll have a 2x plus 3 times an x minus 3 times an x plus 2. Now since it's a leading coefficient, I need to multiply all the leading terms in each binomial to each other. This will give me a 2x to the 4th, but I don't want an x2 to the 4th. I don't want a 2x to the 4th. I want a 9 as my leading coefficient. So I am going to multiply in front of everything by 9 over 2. This will divide with the coefficient in the numerator, and I will have a 9 in front. Now, if you have no idea what I just did, which is possible, let's just say we have 2x to the fourth. We need to multiply that by something that will give me a leading coefficient of 9. Right now, I don't really care about the x to the fourth, I just care about that 2. And so if I want to find out what value a would have to be so that I have a 9 in front, I divide both sides by 2. And a equals 9 halves, and that's my coefficient out front of everything in my polynomial. Now, in example 7, we need to find the polynomial of degree 3 that has zeros, negative 2/5, 1, and a third, and has a constant 10. We'll do the same process as we did before. X equals negative 2/5, x equals 1, and x equals 1/3. Now, instead of making these pretty binomials without any fractions right off, I'm going to just bring the fractions over because I'm curious what my constant term will be. I need my constant term to be 10. That's the last term in the polynomial. So that means that whenever I multiply all the constants to each other, I should get 10. So I might have to change something. I might have to multiply by some number out front so that my last term is 10. I'm going to multiply all these constants to each other. That will be a 2/5 times a negative 1 times a negative 1/3. That's going to give me a 2 over 15. That is clearly not 10, so I have to force this to become a 10 by multiplying by some unknown amount that will make it equal 10 at the end. Multiplying by the reciprocal, 15 over 2 on both sides, gives me a is equal to 150 over 2. So this 150 over 2 is equal to 75. So my polynomial, now with pretty binomials, not fractions, will be 75 out front to make my last term, my constant term, a 10. I will have a 5x plus 2. I will have an x minus 1, and I will have a 3x minus 1.